Hi, everyone. Welcome back. So, we've been talking in the last couple of lectures about equilibria and their linearizations, and also about stability. So, it turns out that stability is kind of part of the picture, but we often want to know a little bit more information about the ways in which an equilibrium may be stable, unstable, or asymptotically stable. So, we have a classification that we can make, at least in the case of two-dimensional systems. And I'd like to go over that in some detail now, basically giving you the pictures that go along with these words. So in two-dimensional systems, whenever we have an equilibrium, we can linearize about that equilibrium, as we covered last time, and then the resulting linear system, which will have a 2x2 matrix in it, has two eigenvalues. And we talked about, we have a theorem 6.4, I believe, 6.3 or 6.4, that tells us about the stability or asymptotic stability of the linearized system based on those eigenvalues. So let's just refine that a little bit more and attach some names to these things. So once we've got to the linearized system, we look at the pair of eigenvalues that we have, and there are several different configurations that they can arrive in. They could both be real and negative, so two negative eigenvalues. In that case, what we have is we know that it's asymptotically stable, and the kind of equilibrium point we have there is called a stable node. So basically, everything is going to converge down to that node in a pretty straightforward fashion. So pictures are coming up on the next slide. Just be patient. If you happen to have them printed out, you can take a look now. So a stable node in that case. If, on the other hand, both of the eigenvalues are positive real numbers, then we get an unstable node. These look exactly the same, except the direction of the arrows is changed. For a stable node, all of the arrows are pointing inward toward the equilibrium. For an unstable node, those arrows are pointing outward. So the system is unstable. The case that we haven't really talked about yet is what if they have opposite signs of each other? If we have one positive eigenvalue and one negative eigenvalue. Well, our theorem tells us that in that situation, the equilibrium is unstable. And what we describe there is called a saddle. And again, the picture is going to make it clearer what's going on there. In the direction, well, when you look at the negative eigenvalue, you will have an eigenvector associated with that, and solutions along that eigenvector will converge toward the equilibrium. But every other solution will eventually go away. So on the whole, if there's even one that goes away, then it's unstable, and since there are almost all of them go away, we have an unstable equilibrium there, a saddle. So the other possibility, if the eigenvalues are not real numbers, then they are complex, and they come in conjugate pairs. So since there are only two eigenvalues in this kind of system, we get a pair of eigenvalues that are complex and no others. If they happen to be purely imaginary, meaning that their real part is equal to 0, then we have a stable but not asymptotically stable situation, and we call that a center. That will be characterized by solutions that rotate around the equilibrium but do not converge to it. And they do that in closed paths. So this was what it looks like a lot of the time in conservative systems. If, however, the complex eigenvalues are not purely imaginary, we could have two different situations we have to distinguish. One is if it is complex and they have negative real part, and the other is if it's complex and they have positive real part. We saw with our theorem last time that the negative real part corresponds with the solution being asymptotically stable, and the positive real part corresponds with the solution being unstable. And the names that we give to these, for reasons that will be apparent when we see the pictures, we call them a stable spiral or an unstable spiral, depending on whether it's stable or not. So negative real part complex numbers get us a stable spiral, everything spiraling in toward the equilibrium, and complex eigenvalues with positive real part give us an unstable spiral, things moving out from the equilibrium in a rotational way. All right, so let's have a picture of some sample systems of what this looks like. So I'm going to go through them again one by one. These are the same cases that we just saw. So again, we look at the stability of these equilibrium points and we're classifying them. In the left column here, we have what happens if we have real eigenvalues. In the right column, we have what if we have complex eigenvalues. and here are our cases. So if the eigenvalues are both positive, then we have an unstable node. So what we're representing here is these arrows with the dashed lines. Those are solutions along in the direction of the eigenvectors associated with one of these eigenvalues. And for simplicity, they're just drawn to be 1, 1 or 1, negative 1. And because the eigenvalues are positive, you're always multiplying by e to the lambda t, which means that things are going to grow. So things move out from the origin, and that's a solution. And this is a solution moving out. And all the other solutions are curved, and don't go along the eigenvalue directions, but they do all move outward. So from the point of view of this equilibrium, anything that starts in a small neighborhood moves outward, so it will be unstable. If we reverse that and we have negative eigenvalues, then we get the same picture, but everything points in. The arrows just change direction, and we get a stable node. So here, if we look at an equilibrium value, which is at the center here, then any initial condition you pick in here, the solutions all move inward, get closer to the equilibrium, so that will be asymptotically stable. We call this a stable node if both of the eigenvalues are negative. If one is positive and one is negative, it's a little bit more complicated. So what we're representing here is we have the eigenvalue direction lambda 1. With the negative eigenvalue, things move in on this direction. But if you notice, every other solution goes away. Something on the other eigenvector direction goes outward, right? These go outward. And anything else might come in this direction. It might get close, but eventually it will curve away. No solutions can move inward like this. And that's basically because they all have a component of this unstable part that moves away. Right? So we have a stable direction and we have an unstable direction. And together that makes this picture of kind of things curving in close and then moving away in the long run. And from this picture, especially if you imagine this in a three-dimensional setting, this is called a saddle. Right? You can kind of see what's going on there. If you want a better idea, there's a three-dimensional graph called the monkey saddle that would give you an idea of why we get this name. Right? Okay, so that's all of the cases with real eigenvalues. We're not going to deal with the cases where one of the lambdas equals 0. Those are the so-called degenerate cases, and those are not going to be so important for us. So we're going to pass over that and not worry about degenerate equilibria at this time. Okay, now suppose instead of having real eigenvalues, we have complex eigenvalues. So lambda equals alpha plus beta I. The alpha is the real part, and we saw in our theorem and in the classification table that we did just a little while ago that it's the real part that determines whether something is stable or not, right? It doesn't actually matter very much what beta is equal to. That will end up dictating the direction and the speed of rotation, but it won't determine the stability. All right, so first case is what if alpha is equal to 0? So the real part is 0. That means we have a purely imaginary eigenvalue, lambda equals beta I, and also lambda equals negative beta I. So, if we wanted to be totally clear here, we might want to replace that plus with plus or minus, right? We have those, but we're going to be considering the positive one just to be definite. That's all that we need to look at. Okay, so if that's the case, we get a center. We have alpha equals 0. So this in the center situation, we have solutions that rotate around the equilibrium at 0, but they don't get any closer. They form closed loops around, right? And that's because they lack that exponential part that would make the magnitude of things either larger or smaller. So we get what's called a center. And the center will be stable, but not asymptotically stable. If the real part is positive, then we get a spiral solution. It may look like it's actually reaching the equilibrium here, but it doesn't do that. It actually we always start just a little bit away. And once you start a little bit away from the equilibrium, solutions will rotate out, right? So if I started here, then I would expect the solutions to move out in this direction. So that is what's called an unstable spiral, or it's sometimes called an unstable focus. Our book calls it a spiral. If alternately the real part is negative, we get the same kind of picture, except the arrows move in the opposite direction. Things will spiral inward. So if I picked an initial point here, it might curve in this way. Remember, different solution curves can never intersect each other. So imagine many of these spirals on top of each other filling up the entire phase plane. So basically, this is the way the linearized system behaves. These are all of the things that can happen. And as a general rule, however the linearized system behaves near an eigenvalue, near an equilibrium, is the same way the nonlinear system will behave near that same equilibrium. The only exception to that rule is the center. The center is kind of on this precarious balance where alpha is exactly equal to 0. So when that happens, sometimes the higher order terms, the not the linear terms, but the second order or third order terms come into things, and they will knock it off of this very delicate balance that makes things loop around. So we can't count on an actual center existing in the nonlinear system. What will happen is the nonlinear system will, most of the time, will actually either behave like an unstable spiral or a stable spiral, basically depending on how this precarious situation in the center is perturbed. So you can't rely on that one translating up to the nonlinear system. So if you do get a center, you should be a little bit careful. All of the other cases, however, if the linearized system is an unstable or stable node, the nonlinear system will also behave that same way. The same thing goes for saddles and all of the spirals. They all translate back up to the big picture. And one of the things that we're going to want to do is, like, the final thing we do in the class is figure out if I have different kinds of eigenvalues or different kinds of equilibria throughout the phase plane of a nonlinear system, then how can I how can I take that and put the different pieces together? If I know that there's a spiral in one place and a node in another place, or a stable node in another place, and maybe a saddle somewhere else, can I put the pieces together to figure out how the different solutions could behave, how those things can be patched together to make a picture of the overall behavior of solutions to the system? That's the ultimate goal. We take these local pictures that we get from linearization and paste them together to get an overall qualitative idea of how the solutions will behave in the system as an entirety. And we'll look a little bit at that in one of the last lectures that we do for next Monday. All right, that's about it.